we're going to share a moment. It'll be beautiful. Talk about the moment of inertia, okay, which is an object's ability to resist changes in rotation, okay? Remember what I went over in the previous video with the record player. Torque causes things to rotate or accelerate rotationally or angularly. If I have a mass on a light string, just like Bob, say hi to Bob. Hi, Bob. He's still with us. This is a mass on a light string, okay? And we will calculate the torque that is on Bob right now. And that amount of torque, again, is a radius multiplied by a force. Okay, now remember, any given force is equal to ma. So my first swappertunity is to call F ma. A. Now, remember that A is the linear or the tangential acceleration specifically, and that linear quantity is related to the rotational quantity by a function of the radius, okay? So that's something else I went over in the last video, is to remind you that that linear or tangential acceleration is the same thing as its rotational acceleration times the radius, or ralpha. So A equals ralpha. So my second swappertunity, quite literally, is turning that A into an R alpha. So the torque being applied to Bob is a radius times a mass times an R alpha. So you put the two R's together, it's mr squared alpha. So torque is equal to mr squared alpha. Please remember that mr squared is a very special quantity, which is what I highlighted the other die. And again, and you can add up all those mr squareds. That I, again, is the mr squared. So if there is more than one Bob on this string, I could have 2 or 3 Bobs from there. They will each have their own M and their own R. Okay, so you could add them all together to get the I of the entire object. So the torque is equal to I alpha. That is Newton's second law, but specific to rotation. It's the same thing as an F equals ma. Remember, that applies to things that move linearly, all right? So remember, rotational quantities have Greek letters in them that correspond to linear quantities. So instead of a distance, it was a theta. Instead of a v, it was an omega. And instead of an a, it's an alpha, right? So this a turns into an alpha. Now the rotational equivalent of mass is I, the moment of inertia. So it's an I times an alpha. There's torque, okay? F equals ma. Torque equals I alpha. Please remember that formula. So what I'm going to do is just give you an example of calculating a moment of inertia. Let's pretend in our headsies we have two masses, one 10 kgs, one 5 kgs. Let's say those two items are connected by a thin rod, and when it says a thin rod, it means you can neglect the mass of the rod. Don't worry about it. It's 1.5 meters long. What is the I about the left axis, or N? So what if I make that the pivot point? The triangle means that's where we're going to rotate around. If that's the case, you can visualize it going around in circles, either in the same plane as the paper, or you could visualize it coming outa and inda and outa and inda and outa and inda, however you care to visualize it. It doesn't matter, but about that left side. Remember, the way you calculate an I is you just add up all the mr squared. So m1 is 10 times its radius. Well, that radius happens to be 0. m2 then is 5 kgs times its radius, which in this example is 1.5. So what all we're going to do, that mr squared goes away to 0. This one is 5 times 1.5, but not just when it's 5 times 1.5 squared. So this ends up being 11, and the letters you write down next to an I are just what you see there. It's a very awkward collection of letters, but it's a kilogram times a meter squared. It's literally just that, because it's a mass times the square of the distance that mass is from the axis of rotation. That's all it is. So you keep that collection of letters. That's it. 11 kilogram meters squared. Now remember, the I will change if I change the axis, the pivot point. So what if I make the I around the right side? What if I want to get rid of that guy and say, well, what if I make that the axis now? This has the same radius, right? But this is the one that dies. This has a larger mass from that same distance away. So the I should get bigger. It's remember, mass inertia is a resistance to change. So if you have more mass, you're going to have more resistance. So this is going to be 10 kgs times 1.5 meters, and that's going to be squared. And the m2 times r2 is what goes away. And in this case, what this ends up equaling is 23 or 22, 23 kilogram times meters squared. Okay, now that should make sense that it's bigger because it's a larger mass and its distance is the same, but the mass went bigger. Now, what if I ask about the I around the center mass? Okay, what is the I about the center mass of this guy? And hopefully you can tell, well, this is a heavier than that, so the center's not going to be right there. It'll be over there somewhere-ish, and that's supposed to be a triangle, sorry. So if the pivot point is the center mass, what I'm going to do is calculate the distance that center mass is from the left side. All right? So that is that calculation. Hopefully you don't need me to show you how to do that. You know how to do that, but here's what that calculation is, the x center mass relative to the left side being 0. 10 kgs times nothing, right? Because it's a mass times a distance, but we don't square it. It's an mr plus the other m times its r, 5 times 1.5, and you divide that by the mass whole, 15. 5 times 1.5, you all know, is 7.5. 10 plus 5, you know, is 7.5 divided by 15. That means our center mass is 0.5 meters away from the left side right there. It's 0.5 meters away from the left. It's 1 meter away from the right. All right. So the 10's distance now is 0.5 meters. The 5's distance now is 1 meter. And so what I'm going to do then is I'm going to go ahead and calculate its I about that center mass by doing these. I will say it is 10 kgs times 0.5 meters. That's squared. Into that I will add 5 kgs, and I will multiply that by 1 meter, and that 1 meter is squared. Okay, that's going to be the I about the center mass. So the I about the center mass of this guy is actually a little smaller. It's 7.5. And that's kilogram meters squared. And it should make sense to you that that I got smaller because the mass got closer to the axis of rotation. If I put the axis in the middle, that brings all that mass closer. And remember, when the radius is small, boy, that resistance to rotation is small. When the radius is big, the resistance to rotation is big. That's why I had those C clamps on the meter sticks the other day showing you how the distance from that affects your ability to rotate. So please remember, the I, you always have to choose a point of rotation. If you get to choose it, then be nice to yourself and choose wisely. Other times you won't be able to get to choose it. The I changes when that axis changes, and another way to think about masses, or I, is just the distribution of mass. It's where is that mass located relative to a pivot point. There are always charts that have I's on them, and it is an mr squared or some fraction in front of it. This is the Blue Book's version of the I chart. So it has, this is mr squared, this is 2/5 of mr squared right there, whatever, but I will show you more of these. So the Blue Book has it on page 251. The Green Book has one that is a little more detailed. It's on page 255. But this chart here, again, is just a bunch of different shapes with different axes of rotation and what their different formulas for I is or are. It's always going to have an mr squared, but sometimes there's a fraction in front of that mr squared. This one happens to be 2/3 mr squared for a hollow sphere. If it's a solid sphere, it happens to be 2/5 mr squared. If it's a hoop rotating, spinning like a coin, it's 1/2 mr squared. If it's a hoop just rolling downhill, it is just mr squared. Okay, so different shapes have different I's. You don't have to memorize them. What you can do, if you ever need to, look up. All I did is just Google moment of inertia chart, and 3,640,000 of them show up. and it will have all kinds of I's for you. You can do that when you need to, unless the problem says, hey, calculate the I. All right, so feel free to look those up. Another thing to tell you about is something called a parallel axis theorem. It means you can combine I. Sometimes you got two I's. If this thing is rotating like this, right, it's got a certain I through the center mass. But if it's spinning around something like that, it will behave differently, and that is going to be parallel to that center mass, which is why I taped an orange to a pencil. So that's a teacher who cars right there. All right. I did that on purpose. It's a good thing we passed a levy, or this wouldn't be possible. But what I want you to realize is if this orange were just rolling downhill, then the axis that it rotates around would be its center. So if it's just spinning around its center, then that's the center mass right there. It would just roll through and in. But can you tell if it's doing one of these, that it's rotating around the pencil now, and the pencil is parallel to the center mass of the orange, isn't it? If it's parallel to the axis through the center mass, you have something called a parallel axis theorem. So if I were to calculate the I for that orange rotating around the pencil, it will be different than if it were an I rotating, or an orange rotating around its center mass. All right. So that's what they're trying to show for you here. The I then is this I equals the I about the CM plus the parallel axis. All right. The I about the center mass for a solid sphere is what I showed you in that book. The I about the center mass of a solid sphere is 2/5 mr squared, okay? That's just something you can look up. You'll always have access to it, or the problem will be, hey, use calculus to figure it out. I'll show you in a future video. The parallel axis then, again, was what was highlighted in orange. It's just plus an md squared. The m is the mass of the orange, so it's the same m, and had the d is the distance that axis is from the center mass axis, which in this case is just another r, and that is squared too. So it's a 2/5 mr squared plus another mr squared. So I will add those together. I'm going to put a fraction in front of this to make it have something in common with 2/5. But if you call this 5/5 mr squared and add 2/5 to 5/5, you end up getting the I being 7/5 mr squared. So using the parallel axis, if they were to say, hey, what's the I about that? Now remember, those I's change and different shapes have different guys. So this guy has just a plain old mr squared. It's the same as this guy's resistance to rotation. It's just an mr squared. They didn't show you this in those data tables, but remember, can you tell if I go really fast with Bob here, what his mass ends up looking like is this? It's the same thing. So remember what I said smart is. It's the ability to look at Bob and see a roll of tape, quite literally. I mean, look at one thing and see something else. Other times, it's hard to tell if a cylinder is solid or if it is hollow. Like these, which you're not getting. Good Lord, this stuff is like gold right now. I had to elbow 3 ladies in their 60s to get this thing. Okay, I'm just teasing. They were probably in their 90s. But anyway, is this a solid or a hollow cylinder? And it just depends. But what I would say is the way you'll end up calculating it, and I'll show you, is you'll basically kind of average the square of the radiuses. So it would be this radius plus that radius divided by 2, but you'll end up having it squared because it's an mr squared formula. So this, sometimes you'll have to account for the fact that there are 2 radiuses, and that's just, again, but it's, think of it loosely as the average, okay? Don't subtract this one from that one. That's what a lot of students do. But it's not the difference in the 2 radiuses, okay? Which is actually what they're showing you, if you can see it right there. But anywho, I will show you the math on how to do some of those I's, calculus, lie, here in a bit. But what I'm going to have you guys do is from the green book. Okay, chapter 10, there'll be 37, 45, 47, and 69. Okay, those 4 out of the green book. I'll post pictures of them. But anywho, I'm coming up on 15 minutes. We just had a moment, didn't we? Yay, physics.